In this video, we're going to do an example of a curve sketching problem, and in particular, we're going to sketch f of x equal to the square root of x squared plus x, quantity minus x. Anytime we do a curve sketching problem, the first thing we want to do is we want to determine the domain. In this case here, that means we need x squared plus x to be equal or greater than 0 for x to be in our domain, because we can't have a negative inside the radical. This is equivalent to x times x plus 1 is equal or greater than 0. And this breaks up negative infinity to positive infinity into 3 intervals, which we need to check to see if they are greater than 0 or less than 0. And so we'll do that now by plugging in some values in each of those intervals. And when we do that, we see that this is a positive, negative, positive, which tells us the domain of f is negative infinity to negative 1 inclusive, union 0 inclusive to infinity. And this is our domain. We then need to calculate some limits. Well, for vertical asymptotes, we need the limit as x approaches a from the left or the right to be positive or negative infinity. And that does not happen in this problem, so there are no vertical asymptotes. For a horizontal asymptote, we need the limit as x approaches either infinity or negative infinity of our function to equal a finite value. Let's go ahead and do the limit as x approaches positive infinity first. And here our technique for that will be to multiply by the conjugate of this over the conjugate of this thing. And in a sense, we are going to reverse rationalize the denominator. And so let's go ahead and do that now. We can think about also why might we need to do this. Well, if we put in really big values here, we get a positive, we take the square root of that, and we get something that's going towards infinity. If we plug in really big values here, we get something that is subtracting away but going towards infinity. So we get something going towards infinity minus something that's going towards infinity, and we don't know what that really means. So here our technique is to rationalize or unrationalize the denominator in a sense. So once we do that, we end up with this should be x squared plus x minus x squared all over this radical and then plus x. Notice that these cancel, and we also want to factor out an x out of this denominator. So how do we do that? Well, inside the radical here, we would need to factor out an x squared, since x is actually the square root of x squared. So we had to pull out a square root of x squared there. Or at least that was true. X is equal to the square root of x squared when x is positive. Okay. And now that we've done, that is supposed to be 1 plus 1 over x. Right? We factored out an x squared out of x squared, we get 1. We factored out an x squared out of x, and we get 1 over x left over. All right. Once we do that, we can factor out an x out of each of these terms. Right? We factor out an x out of each of these two terms here, and then x cancels with that. And what we're left with is a 1 over square root of 1 plus 1 over x plus 1. The limit as x goes to infinity of 1 over x is 0. So this becomes 1 over root 1 plus 1, which is 2. So we get 1/2 here. Really quick, limit as x approaches negative infinity. We get something that is square root of a positive value when we plug in really big but negative values into here. So we get a positive value here. Minus a negative means we get positive values here, and these are shooting off towards infinity. So we get a positive plus something going off towards positive infinity now. And so this whole thing shoots off towards positive infinity if x is approaching negative infinity. So we don't need to run through that calculation. But again, we do have one horizontal asymptote at y equals 1/2 as x approaches positive infinity. Now we need to find the first derivative so we can find intervals of increase and decrease, and the second derivative so we can find intervals of concavity. Our function is square root of x squared plus x minus x. So the derivative of square root of x squared plus x is 1/2 times x squared plus x to the negative 1/2 times the derivative of the inside, which is 2x plus 1, right, by the chain rule. And then we just need to take the derivative of the minus x part, so this is minus 1. We want to set that equal to 0, so we end up with 2x plus 1 all over 2 root x squared plus x is equal to 1, or 2x plus 1 is equal to 2 root x squared plus x. Okay? And then we can square both sides here to get 4x squared plus 4x plus 1 is equal to 4 times quantity x squared plus x, which gives us 4x squared plus 4x on the right. And when we cancel all of these, we get 1 is equal to 0, which tells us there is no solution. So we don't gain any extra critical values. And for our intervals, all we have are still the intervals from negative infinity to negative 1 and 0 to infinity. Right? We don't have anything going on between negative 1 and 0 because our domain, this isn't in our domain. So now we need to plug in something between negative infinity and negative 1 into our derivative up here to determine if our function is increasing or decreasing. Well, if we plug in a negative, something bigger than negative 1 at least, or more negative than negative 1, we get a negative up in the numerator, and the denominator is a positive, so we get a negative in this term. Minus 1 is certainly a negative value. So this is negative, which tells us we are decreasing. And over here, between 0 and infinity, let's plug in something like 1. We get 2 times 1 plus 1, so this is 3. All over 1 plus 1, so the square root of 2 times 2. Square root of 2 is about 1.4, times 2 is 2.8. So we get 3 over 2.8 is a little bit bigger than 1. So when we subtract 1, we get a positive. So we are increasing on that interval. Very good. Let's move on and do the second derivative now. All right. The second derivative here, we take the derivative of negative 1, that's just going to go to 0. So we need to then take the derivative of this term right here. So we get the denominator. Let's do that. Times the derivative of the numerator, which is just 2, minus the numerator, times the derivative of the denominator, which is 2 times 1/2 times x squared plus x to the negative 1/2 times 2x plus 1 all over 4x squared plus 4x. Actually, let's not write it like that. Let's write it as 4 times x squared plus x. Right? We just squared the denominator there. Now we have a messy piece here with the root x squared plus x, and then over here a root x squared plus x in the denominator. So we're going to multiply by root x squared plus x in the numerator and denominator to help reduce this. This distributes to both terms up here, and so we get 4 times x squared plus x minus 2x plus 1 times 2x plus 1 is 2x plus 1 squared all over 4 times x squared plus x to the 3 halves. This in the numerator reduces down to -1 all over 4 times x squared plus x to the 3 halves. Right? Just multiply this out. You get 4x squared plus 4x plus 1 again. We're subtracting all of that away. So the 4x squared plus 4x is cancel. And then we just have a -1 left over in that numerator. So finally, we can again determine that, well, this is actually... everywhere this is negative, because remember between -1 and 0 we do not even have, that's not even in our domain. So every other value we get a negative over something that ends up being positive down here. So this is concave down everywhere. Yeah, this is just concave down everywhere, since we get a negative over a positive for anything that we can plug in our domain. All right. Well, what does that tell us? That tells us that when we draw this graph, we have a few points that we want to make sure we get down. First off, 0, 0 is a coordinate point and was the endpoint of one of our intervals. And when we plug in -1, we get +1, so that's the other endpoint of our interval that is in our domain. From -infinity to -1, we are concave down and decreasing. So that looks like this, as well as knowing that this shoots off towards positive infinity as x goes towards -infinity. Then, as x goes towards positive infinity, so over here from 0 to infinity, we are increasing but concave down, and also we limit to y equals 1/2. So this will look like that. And that concludes this curve sketching problem.